With the basics of fractional linear transformations out of the way, in this video we're going to talk about some further properties. So we're going to talk about how to factor fractional linear transformations into translations, multiplications, and inversions. We'll talk about an interesting interpolation theorem, and we'll talk about mapping properties of fractional linear transformations, namely the property that they send circles or lines to circles or lines, which I've written here as the silly name clerkles. Now let's talk about the first basic property, the following theorem, which says every fractional linear transformation can be written as a composition of translations, multiplications, and inversions. So the proof is actually quite easy. It just uses some facts about matrices. So we take our FLT F and we write it using a matrix A in GL2C. And now we just use the fact that every invertible matrix is a product of elementary matrices. So this is just something you learn in linear algebra. Here are the elementary matrices. We usually think of them in terms of row operations. The first one amounts to the row operation where you add A times the second row to the first row. But in any case, if you convert this into a fractional linear transformation, this becomes translation by A, which let me just give this the name T sub A for right now. The next operation, which is swapping two rows, amounts to the FLT of inversion, which I'll just call J because it would be too confusing to use I. The next elementary matrix is where you multiply the first row by A, and you do need A to be non-zero. And this gives you a multiplication operation, so I'll just call this MA. And there are a couple other row operations I left out, namely multiplying the first row by A and adding that to the second row is this operation here, but this one can be written in terms of the ones we've already presented. So you can swap two rows, do the first row operation, and then swap the rows again. So this one can be written as J, TA, J. And also you could multiply the second row by A, but within PSL2C, multiplying the second row by A, well, you could factor A out of this whole matrix, and it amounts to the same matrix in PSL2C, and so it amounts to just multiplication by A inverse. So every elementary matrix corresponds to either translation, inversion, or multiplication, or some product of these, and therefore every fractional linear transformation can be written as a composition of translation, inversion, and multiplication. Now let's look at a quick example to just illustrate this. Again, I'll do it with the Cayley transform for no particular reason. And this, I don't want to go into too much detail because this is just basic linear algebra stuff, but it might be a little useful to see this done concretely. So here's our FLT written in its initial form, but we can write this as FA using the matrix A right here. And we perform row operations to this to convert it to the identity, and I'm going to keep track of all the row operations. So I do -I times row 1 and put that into row 1 spot. That's my first operation. And I do a bunch of these until I get to the identity. And I keep track of the row operations. And this is something you do in linear algebra, which is each elementary matrix corresponds to a row operation, and when I apply these in succession, I'll get the identity. So then A here can be written as these inverse elementary matrices, and I've just written out what they are right here. And if you want to write FA as a composition of multiplications, translations, and inversions, well, you just have to write, do the conversion. So this first one was translation by 1, so I put a T1. The next one was multiplying the second row by 2, which I said you can convert that into multiplying the first row by 1/2 because we're in PSL2C, so I can put that here. This was the next one was one of these row operations that I had to do a little conversion to get it into inversion and translation. So it's J, TA, J. So in this case, I'll have inversion, T minus 1, J, and then the last one is multiplication by I. So I'm not claiming this is the fewest number of factors, and this factorization is by no means unique, but by just doing standard operations with elementary matrices, you can factor a fractional linear transformation into these three standard types.